So here we can see our very first moment problem as we would encounter it in real life. It's a pipe structure with three forces attached to them. And we now have to find the moment acting at point O. Let's read the problem statement. Determine the moment or the force system resultant that is acting at location O, right here, due to the three forces acting at the pipe structure. 1, 2, 3 forces, 300 Newton, 500 Newton, and 600 Newton, acting at a specific distance. The distances are indicated here. And my experience in the classroom is that 50% of us can solve this right away with the knowledge we just created through the lecture, whereas the other 50% struggle with it. And there's no good or bad with being able to solve it at this point or not. But I personally believe that it's always good to challenge yourself and struggle with it a little bit before I will present the solution to you. So therefore, I encourage you to do the same thing that we would do in the classroom right now. Just go ahead and give it a try. And again, my experience is that students have an easy time with understanding how much moment this force here produces, but then these two become a little bit tricky. And I encourage you, because it's really like a 5-minute problem once you understand it. Don't get me wrong, it shouldn't be 5 minutes for you right now if you don't understand it. But ultimately, it's a 5-minute problem. And therefore, I encourage you to just go ahead and give it a try. Pause the video and then come back for the solution to match it up. There's no harm in getting it wrong. In fact, you should get it wrong right now just so that we can develop the right solution together. And so you will get it right on the exams and the quizzes. So pause the video and I'll see you in just a second. All right, welcome back to the solution to this problem. Let's think about what we need to do. We need to find the moment at this point. And as we know from before, the moment about point O is equal to the sum of the forces times their perpendicular distances, right? So that's kind of our formula. And of course, we identified counterclockwise positive. Now let's look at this picture. So this force has a lever arm, which is often obvious to students with 1 meter. And so it would be 600 times 1. I will write that down in a second. But it becomes a little bit more complicated for this and this one. But just take a look at this formula and think about the perpendicular distance, and then a sketch goes a long way. I will now go ahead and calculate or draw in these distances. So for the first one, we already know that this distance would be, let's call it D1 perpendicular. And for the second one, it probably is also still easy because I have this distance here. And that would go in this direction. So this would be for the 500. So this would be D2, let's say, perpendicular. And for the third one, it's the 300, which now causes confusion often to students, right? But it's in reality, it's nothing different than the same thing. And if you struggle with it, just rotate your page by 90 degrees and understand that we're looking at this distance because that is the perpendicular distance from here to here. So I call that D3 perpendicular. And now I can go ahead and calculate that. And by the way, this is difficult to show now because I only have the screen here. But in the classroom, I always tell my students, hey, when I need to understand if it's a positive or a negative moment, what I do is I pretend my left finger has a needle and I place the left finger, my left index finger right here, and I poke the needle into the piece of paper. And then I take my force, which in this case is pointing downwards, and I use my right hand or my pencil in my hand and pretty much align it with the force and then rotate it on a string that I connect between the pen and the needle that I poked into the page, and then rotate it, of course, in the direction that the force is pointing. So what would that mean? That would mean that this force is rotating this way around. Let's do that for the second one. So this force here, if I put a needle here, and actually I have a line of action here, let me show you that as well, because I can really do that anywhere. So I have a line of action that really is in this direction. And so if I poke a needle here, then I have a string that connects the line of action and this one, and my line of action goes in that direction. So therefore it would rotate in this direction, right? Which would be counterclockwise. So that would be positive. Similarly, for the 300, I poke a needle here. I have a string that connects the line of action. So that would be here. And then I rotate in the direction of the force, which in this case would go down this way. So that would be clockwise. And you will see that now in my solution. So first of all, my m about O is equal to F1 times D1 perpendicular. Now that turns clockwise, therefore it's negative. All right, remember that moments are defined counterclockwise positive. And by the way, this is not part of the equation, so therefore I leave that out. All right, and then my F2, which is the 500, so F2, which rotates counterclockwise, therefore it's positive, times D2 perpendicular, and my F3 times D3 perpendicular, and that one rotates, and now I have to think about it myself, so it's rotating clockwise, therefore it's negative. All right, now let's put numbers to it. And I think at this point it's just mathematics, so that should become easy. So minus F1, which is 600 Newton, multiplied by the lever arm, which was 1 meter. Then we have plus F2, which was 500, right? 500 Newton. And now, of course, it depends on your geometric understanding. But ultimately, what I have is 1 meter plus 2 meters plus 2.5 times the cosine of 45, right? 2.5 cosine 45. And of course, I understand that cosine and sine is really the same for 45-degree angles, but I want to make sure that we understand that we're talking about the component here on the bottom. And let me, for clarity, also add that so that we understand that we're talking about this distance here, which is really 2.5 times the cosine of 45, and of course that's in meters, and so I shouldn't forget that here on the bottom either. But now I have that component complete, and I need my last component, which is the 300 newtons, and that was negative, so minus 300 newtons. And of course you already guessed what the lever arm is. It's times 2.5 meters multiplied by the sine of 45. So that is technically everything we need to come up with the final result here. But before we do that, let me zoom in and clarify where that distance is coming from. So I'm going to use my ruler and probably best show it here because that's where the triangle starts. And I'll show you that this is 2.5 meters times sine of 45. Again, sine and cosine makes no difference, but this is the correct way of thinking about this, in my opinion. So now it's just a question of plug and chug, or actually like chugging because we already plugged it. So what we will find is that our moment actually is positive 1,254 Newton meter. And there are two important things here to understand. Number one is that it's Newton meter. It's force times distance. That's how our units always are for moment calculations. And then also that we set plus here, because the plus tells us more than just it's a positive number. It also tells us that we're dealing with a counterclockwise moment. And that is part of my answer. I always have to identify that. So this entire line here is my answer, and therefore I provide the answer key. And you see that once you study these types of problems, they are fairly quick, right? It doesn't take a lot of time to do this. Of course, while you learn it, it takes some time to understand what is clockwise, what is counterclockwise, what is perpendicular, what is not perpendicular, and so on. But once you get there, this problem, which could be a nice problem on an exam or a quiz, should really not take you more than 5 minutes at maximum. But of course, right now you are in the learning stage, and therefore don't be hard on yourself if it takes you longer. In fact, let it take longer so that ultimately when it comes time to the test, you actually know how to do it under short time periods. But that concludes this problem, and we are now ready to move on to a little bit more complex problem. Here we go for our second problem about moments in planar systems or 2D systems. So what we have here is a cantilever beam that could be made from wood and has three forces attached. One that pushes down on it, one that pulls on it, and one that pulls or rotates it down. And so now we are asked to calculate the moment at A, so that's this point here, which is produced by these forces. So let's go ahead and do that, and let's memorize again that our moment is really equal to the sum of the forces times their perpendicular distances, right? So I now have to look at these forces and really break them down into their perpendicular components. That I believe is easier in this case. So I, of course, could take this force and extend its line of action. Let me show that to you graphically. So let's say I have a line of action here, and I could, of course, find its distance to the point of interest, which would be this one, and I'm going to call this R perpendicular. But that would be really difficult to do for all these forces. In this case, it's really easier to break the forces down into perpendicular and horizontal, perpendicular and parallel components, or vertical and horizontal components. So let's go ahead and actually turn the forces into perpendicular components. So let's get started with the 150 newtons here, and let's clarify that we have a force that's acting in this direction downwards, and that would be, let's call it F1 perpendicular, which that of course would be equal to what? 150 divided by 5 multiplied by 4. So that would be 30 times 4, which is 120 pounds. And of course, I could now go ahead and calculate the parallel component or the x component, right? So this here would be F1, let's call it x, or also parallel. And you do not need to calculate that because it actually passes, the line of action of this force passes through the point of interest. And therefore, we do not need that information. I'm going to skip that and move on right to the next force. And you can already see that the next force, 50 pounds, has the same effect. So the line of action passes through that point. I don't need to do anything with that. However, the force up here, I need to do something with that. So let's break those down, and let's understand that we have a vertical component, which is here. So let's call that F3, and we'll call that F3y because it's in the y-axis. And then we have also this component here, which is F3x. And F3x, for example, would be equal to 100 divided by 5 multiplied by 4. So that would be 100 divided by 5 is 20 times 4 is 80 pounds. And so then here we have 100 divided by 5, 20 times 3, if I'm not mistaken, is equal to 60 pounds. All right, and so now we have all our forces that we need. And last but not least, I need a rotational sense. So again, this is very difficult to show, and like if I only have the screen here available. But let's imagine this once again, where I put a needle into my point of interest and then I connect a string to the force. So this force F1 actually rotates about that point clockwise. So that would be negative. This force here, F3, also turns clockwise. Therefore, that's negative as well. But then F3x actually has a line of action that goes in this direction. So it has a distance like that. If I poke my needle in here and have my rubber band or my string connected to that, I would find that it turns counterclockwise. Therefore, it's positive. Let's write that down. So let's write down M of A about the z-axis, of course, is equal to F1, which is 120 pounds, multiplied by 3 feet. That's that lever arm. And we said that's turning clockwise, therefore it's negative. Now I need to worry about the 60 pounds. So 60 pounds from F3 multiplied by 3 plus 3 feet. That's the lever arm. And that turns also clockwise, therefore it's also negative. But last but not least, I have the X component, which is 80 pounds. 80 pounds multiplied by, be careful now, 1 foot. And that turns counterclockwise, therefore it's positive. And so that 1 foot is this distance here really, because I have a line of action that goes here and then connects the perpendicular distance to A with 1 foot. And that is everything we need. So you see, it's once again just a single one-liner. And the result that we find for this one is minus 640 pounds. So minus 640 pound-foot. Pound-foot. And that is our result. And the minus tells us what? Exactly. It tells us that it's clockwise. So this is a clockwise moment, which is part of my answer. And I, of course, need to state my answer error. And that already solves this problem, which can be a quick solve, but can also be overwhelming if this concept of the right angled lever arm is not understood, or the right angled force, if you will. And once again, I didn't have to worry about the 50 pounds here and this component. I didn't even calculate it because it passes right through the point of interest. Be careful. Often students think that, hey, this is going in the negative direction, therefore it's a negative rotation, which you can see here is already not true. But this can be deceiving, because if this thing was built upside down, so let's say you have this force F3 acting down here with, let's say, 80 pounds. So if you have 80 pounds pushing to the left down here, then it would actually rotate clockwise, right? And therefore it then would become negative. Whereas if it's acting up here, it rotates counterclockwise, which is why it's positive here. So you see that this sign here, this and this sign, has nothing to do with the direction the force is pointing into. So it's not like, so for example, here we have 120, and you could argue, hey, 120 is going down in the y direction. That's an argument I often hear in the classroom. But that is not related at all. The rotational sense is the only thing that matters. So it only matters what rotation you have about this point. And in this case, you have a force that isn't going negatively down, but it actually rotates clockwise, and therefore it's negative. And that is the reason why you see this negative. Not because the force is pointing downwards, but because the force is rotating clockwise. So this can be deceiving, as I said, right? So for example, if this force was going downwards on this side, then it would actually rotate counterclockwise, and therefore it would be positive. So it really has always something to do with the reference point and the point of interest. So please don't confuse direction with rotation. That's very different. But I believe that concludes this problem and tells us everything we need to take away from this. I hope this will help you on your homework and to get you ready for your exams and quizzes. We are now ready to move on to more complex examples. I will see you for those on the next page. So here we have our last lecture example, for which you once again have to find a moment about a specific point, which here is the anchor point A. So you see this is like a steel structure which has 3 forces attached to them, and you need to find the moment about that point. And rather than doing this numerically for you, you should do this on your own. I will now help you to understand these lever arms. So for example, for the first lever arm with the 20 kilonewton, right? 20 kilonewton, that one has a lever arm of, you guessed it, 8 meters, right? So that's the 8 meters lever arm. And that is the distance that is perpendicular from the point of interest to the force. So that's the 8 meters here. Let's look at the 15 kilonewton. The 15 kilonewton has a perpendicular distance of 1.5 meters. So the 15 kilonewton has a lever arm of 1.5 meters. And now we have the last force left there. I will break that down for you. I have a force that goes in this direction, which is 50 divided by 5 multiplied by 3. So that's effectively 30. And then I have also one that is going down, and that is equal to 40, therefore. So let's do the 30 first. So what is the 30 kilonewtons lever arm? That has a lever arm of 8 plus 2 plus 1. And that, of course, is also in meters. And that would mean that we're looking at this point here for 30, right? 30 has a line of action that is along this line here. And the perpendicular distance to that would be from here to here, which is 8 plus 2 plus 1. So we're looking at 11 meters here. And then last but not least, we have the 40 kilonewton. So 40 kilonewton has a lever arm of 1.5 plus 3. 1.5 plus 3 meters. And that is the distance from this force to this perpendicular lever arm, because you might as well have a line of action that goes all the way down here, which then would intersect with the x-axis. And so you have this perpendicular distance. So last but not least, you need to identify the rotational sense. That is the difficult one, I guess. The lever arms become easier and easier the more problems you solve. So let's look at the 20 here. If we rotate about this point, then we would rotate this way around, which would make that counterclockwise. So that would be, I believe, positive. So let's say rotation. And the first one would be counterclockwise, so positive. Now the 15 Newton is acting in which direction? It's acting downwards, so that rotates this way around, which makes it clockwise. Therefore, that is negative. The 30 is the next one. So the 30 would be this force here, which rotates this way around, which is clockwise. Therefore, that is also negative. And last but not least, the 40, which is rotating this way around, that's also negative. So you see the majority of the lever arms are negative here. And that will most likely end up with a negative moment as a result, which would then mean that this would be clockwise, right? So this would be clockwise, 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 and this here would be counterclockwise. So positive counterclockwise, negative clockwise. And I believe the numbers you can run yourself. This is all you need from me to help you solve this problem. I wish you good luck with that, and I definitely encourage you to really solve this, because I believe one of your homework problems is very similar to that. But we will talk about that next.